Right. Oh, well, thanks for coming. So, last GeoWeb lecture, so going to touch on the Geosemantic Web, although most of it's just the semantic web, and then a little bit on the Geosemantic Web, which is just the geographical implementation, or the implementation of geographical web on data on the semantic web. So just to, well, I'll explain what the semantic web is in at the moment, but to say the semantic web is emerging from being a sort of experimental, developmental world into being an actually being used now, I would say. There's quite a lot of data that's available out on the semantic web, and increasingly there are applications being developed that use that data. But it is still a small niche solution at the moment. So most data is not on the semantic web. There are relatively few applications that use semantic data on the semantic web, but it's growing, and it potentially is where we'll be in 10 to 15 years' time. I suspect it's going to take a while to take it. Anyway, so again, I can't see the screen, so I'll have to stare at the thing. Again, so we've mostly been dealing with the World Wide Web so far. So that's a web of unstructured and semi-structured documents, written in HTML, but also involving database APIs. But all the APIs are different. They all have different syntax, etc., etc. And while the various web applications we've been talking about bring together often data from different places, overall, data is unconnected. So, for example, you want to find a hotel near a national park. Now there are applications that will do this for you, but you have to be in the right unit. You have to have the right data connected to do it. So, to take that as an example, you perhaps need to go to the sites about national parks, find out what national park you want to go to, then go to hotel sites, try and find a hotel that you're interested in, and then try and work out whether the distance to the national park from the hotel is reasonable or not. Now, of course, there are applications that can do that for you, but you can appreciate that in certain parts of the world, for example, this information, if it's there, even if it's available, remains separate. As another example, classic example, information on planets. Information on planets is spread all over the place, various astronomy and astrology sites, and they differ in the content that they contain. For example, on some sites, Pluto will be a planet, classified as a planet. On other sites, it won't be. The other thing about the World Wide Web is that the HTML is for human consumption. It's for human beings to read. It's not really for computers to read, despite the fact they can read HTML. It's not a very useful thing for them to read. And the other thing about the World Wide Web is, let's get rid of that fuzzy noise. Nope. Still fuzzy noise. What? That wasn't the plan. The other thing about the World Wide Web is that anyone can say anything about any topic, which is the AAA concept, and we'll just see a bit more about that. So a bit more on AAA. What are the problems with AAA? Everybody can say anything about anything they like, anything about anything they like. Well, one of the problems, as you probably realize, is that there's a lot of non-unique naming going on. There are many different ways about the same thing, identifying the same thing. For example, my name, I exist in many different, on the web in many different ways. Sometimes I'm David Kidd, sometimes I'm Mr. DM Kidd, sometimes I'm Mr. Dr. David Michael Kidd. So I have multiple, so if somebody's looking for all the information they can about me, they have to a certain extent, search for all these different ways that I've identified myself on the internet. I need to be a bit more consistent. Some of this we dealt with in the previous lecture, but information is often out of date on various sites. It's not maintained, or maybe it's not regularly updated. Data can be simply mistaken. We all make errors. We're all humans, we all make errors. But people make what we could say is generally human errors. We put the wrong data in by accident, but also people believe in falsehoods and are possibly delusional as well. So, for example, people, well, like this, I have no belief in astronomy. Oh, sorry, not astronomy, astrology. I believe in astronomy. I have no belief in astronomy, and people putting up various bits of information on the internet about astronomy are basically dealing in falsehoods, as far as I'm concerned. Sometimes these are sort of accidental or not deliberately falsehoods, but people also put up genuinely incorrect data for various reasons deliberately. And these are what I listed there as liars, malingerers, and vandals, or maligners, not malingerers, it should be the maligners. So people who lie for various reasons, for example, to discredit the opposition, people who sign up to review sites and then give bad reviews about other people's products. So they're lying and maligning potentially about another product. And there's people who simply go in and vandalize things for the entertainment value. People who, or political reasons indeed, sort of editing Wikipedia pages and things like that. Putting falsehoods in Wikipedia pages is not that uncommon. And then, of course, people simply fundamentally disagree on a topic. So there are genuine disagreements. The Pluto is a good example. The International Astronomical Union, or Astronomical Union, says Pluto is not a planet, but the astrologers say Pluto is a planet. They've got an interest in it being a planet. And another thing about the AAA world is that it's an open world. Anybody can see anything about anything at any time. So therefore, there is always potentially more to find. So you're always looking for more information. So to a certain extent, the semantic web is a reaction to some of these issues. And it's an attempt to create a distributed web of data rather than web of documents. This is the idea. And in an analogous way that CSS separates, to a certain extent, separates content from presentation, the idea, to a certain extent, for the semantic web is to separate data from the context in which that data is being presented. Okay? So instead of web pages pointing to each other, for example, data items point to each other. And this is, again, an invention of the amazing guy Tim Berners-Lee, and is a W3C initiative that he proposed, and there's a good, that was the initial article in which he proposed the semantic web. Now, the thing to remember about the semantic web is, while it's a reaction against AAA, it doesn't solve the AAA problem to a certain degree. It doesn't get rid of it. The semantic web, AAA still applies, but you've at least got tools and ways of dealing with it. It's about dealing with anybody can say anything about anything, a problem. So what is semantic? Let's just have a quick recap. Hopefully you know this. So semantics is about meaning. It's about what things mean. So we distinguish that from syntax, which is how we structure things. The rules for how information is structured is syntax. So how you write HTML. HTML is a syntax. You have tags on either side, and those are the rules that you follow for writing it. Semantics is what the information actually means. So this is slightly more, a rather deeper thing. What does it mean? And we're also going to deal with semantics, what information means, but we're also going to deal with what things called ontologies, or touch on things called ontologies. Do you know ontologies? Excellent. Excellent. Ontologies in this context, because it's used in many different contexts, is basically the way in which is that you develop a formal model of the world which is based on these semantic statements. So we make semantic statements, statements of meaning, then we combine those statements of meaning to create a model, a formal model of how the world works, how we think the world works. Well, a conceptual model is like a very fuzzy, high-end view of the world. It's like a sort of general hand-wavy statement, pretty picture diagram. It's sort of an overview. This is quite the opposite. It's a model. They're both models of the world, but this is highly structured, completely logical model. Okay, it's structured from statements, so it's like a computer program model of the world. Okay, and these models or ontologies constrain the range of valid semantic statements that you can make. Now, this is probably going a bit hard to take, but we've got practical examples of this in a minute. It allows you to explain or make predictions across your data on the basis of the model that you believe that you use to define the data and control the data. And it allows you to combine multiple models of the world into a single model, so to sort of integrate different people's views of how the world works. So it's got a lot of big, highfalutin names. As I say, it's yet to be decided how well it delivers these. Okay, so quickly. So the contents of the module of this lecture, basically, having had that sort of high-level introduction, is the data structures and the syntax of the semantic web, which is through what are called RDF triples. We've met triples briefly before, so we'll revisit triples. Then I'll talk briefly about how you query the RDF triple graphs that we build, and there's a query language called Sparkle, which is the SQL equivalent of SQL for the semantic web. And then briefly introduce the geosemantic web and finish off by thinking about thinking about mapping the internet a little bit. Okay, so the semantic web is basically built from what are called RDF triples. RDF stands for Resource Description Framework. Okay, but I can never remember what it stands for, but RDF, Resource Description Framework. And the resources referred to are anything that we might want to talk about. So we're going to do a lot of examples because they come out of a book about Shakespeare. So one of the things we might want to talk about is Shakespeare. One of them is Stratford upon Avon, where he lived. But we also might want to talk about the value of X, or all the cows in Texas. So we can, we can talk about these resources are anything that we want to talk about. And the basic unit of the semantic web is the triple. And the triple has the format, subject, predicate, and object. Okay? So here's an example. Shakespeare wrote Hamlet, the play Hamlet. So subject, predicate, object. And this is a directed graph. So it goes this way. Shakespeare wrote Hamlet. It does not allow us to go the other way. Hamlet was written by Shakespeare. No. I mean, that's true, but the RDF does not allow us to do that at the moment. Shakespeare wrote Hamlet, one-way directed graph. And we can combine triples to form large graphs across which we can reason. This is graph database, basically, or graph models of the world. Okay, did we go? Oops. Right. Okay, so as we know, a lot of data is stored in tables. That's what the relational model was all about. So here's an example of a table of Elizabethan literature and music. Title, ID, title, as you like it, author, Shakespeare, medium, whether it's a play or a poem or a song, and the year it was published. That's kind of where you're highly used to seeing data in this format. But we can turn these really easily. Tables can be turned into triples very simply. So, for example, here's some sample triples that have been extracted out of that table there. So, Shakespeare wrote King Lear. Okay, so we've got, well, we don't have King Lear up there, that's not the greatest example, is it? But you get the principle. Shakespeare wrote Macbeth, is the same, contains some of the information that should be in that table, but in fact isn't. It's just got different examples. As You Like It, Shakespeare play, okay? So we know that the columns, we know the title of the thing that was written, we know the author, and we know that the table is about writing. Yep. So it's easy enough to extract out these triples. And we got some example other triples here. So we've got things about what Shakespeare wrote or who wrote what, but we've also got some information on other things. For example, Anne Hathaway married Shakespeare. She was Shakespeare's wife. Shakespeare lived in Stratford, not East London, but Stratford upon Avon. Stratford is in England. Macbeth is set in Scotland. And England is part of the UK, and Scotland is part of the UK. Okay. So we can take tabular information, for example, and convert them relatively easily into a set of triples. And we can take the triples themselves. Here they are just as a table of triples, but it's more sensible to, they exist as a graph. This is the whole point of it. So we can take these set of triples, that defines this graph, where we've got our predicates, being the connecting arrows, and the subjects and objects being the individual items that we're making statements of. And those individual items can sometimes be subjects, sometimes be objects. It depends on their context that they're being used. So Anne Hathaway married Shakespeare. Shakespeare wrote King Lear. He also wrote Macbeth. He lived in Stratford. Stratford is in England. Macbeth is set in Scotland, and they're both parts of the United Kingdom. Okay, so we've got a basic knowledge graph there. So that's great. But of course, we're getting information potentially from different locations. The whole point of this is to integrate information from different locations and to be able to make inferences across those different graphs. So here's some examples. Here we've got some triples about Shakespeare, and here's some triples about the United Kingdom. So we know that Scotland is part of the UK, basically identifying each of the various parts of the United Kingdom, or within the United Kingdom. And we can take those two sets of triples and combine them into a single graph. But one of the problems we have with doing that is we have to decide when is the node in one graph the same as the node in the other graph, because that's how we connect them together, when they're the same. But we don't, the problem is, when are they the same? So one way we can do it, or the way we do it, the way they do it in the semantic web, is to effectively use a global unique identifier, and that global unique identifier is a URL, a web address. And basically, if both graph objects in the graph, both items in the graph, point to the same URL, then they're the same thing. So we make URIs are unique, so we can make, if we both point at the same location, and that location doesn't change, it's stuck there, it's fixed, then we can infer that the nodes, those nodes that have come from different graphs are the same, and we can collapse them together. So here's the example. These are the two graphs, and they've been collapsed together. Okay, so we've got common nodes for England, Scotland. We had two versions. We had two ones, one from the geography graph, one from the Shakespeare graph. So because we've identified which nodes are the same, we just collapse those together, and we can combine the two graphs relatively simply. So we've now got a slightly more complicated graph. It's got some additional plays in. So we've got Anne Hathaway married Shakespeare, who wrote all these graphs, which was set in Scotland. He lived in Stratford, England, part of the UK. But we've also got the other information about the other parts of the UK now included. And that's basically how it works. And there's a lot of complicated maths and databases and sorting out behind that. So how do we actually represent this information in a computer? Well, one of the things that we often use to represent this information is things called Q names. And Q names is basically a shorthand notation for writing triples. Basically, URIs can be quite long to write. They've got a full web address is quite a long thing to write. So rather than write those, we tend to use Q names which refer to URIs. It's just quicker. So we've met Q names kind of before, although we didn't call them Q names. So there's a namespace, colon, and then an identifier. Remember this from tags. It's very similar to tags. So the geo namespace, followed by the identifier England, for example. And in our file, and we'll see the files in a minute, that contain our Q names, we have a declaration at the top of the file which tells us which namespace we're referring to, and the namespace is basically a URI, defined by the URI. And there's a convention of writing in what's called camel case, capitals starting for each one of the words. So everything in the semantic web should be written like this. All right. So what does it actually look like? Oh, there's a Q names table. So instead of writing out the full URL, what you tend to write is things like this. So we've got the namespace lit, containing information about literature. In this case, we've got a subject space, Shakespeare, lit wrote, and then from the lit namespace, we've got the names of the various plays that were written. So this is a convenient way of writing that information. We should have an example. Okay, what I'll do is I'll just go forwards a bit and then I'll go back because I think it's you want to actually see these things, how they're written out. So how are they actually written out, these things? How are these triples written? Well, they're generally written as text files. This is how it's kind of like a form of XML it's written. In fact, there is an XML version of it. So here, for example, is an example of some triples in what's called the N triples format. So here we go. Here's a one web address. This is involving the full web address. And they can be written out like this. They could also be written, I'll give a better example down here. Here's another example called R notation, R3 or N3 notation. So here we go. So if we read this, here's our sort of namespace where it's pointing to. That's the namespaces. So the prefix P is pointing to this namespace. The prefix M is pointing to the meeting organization's namespace. Then we've got our subject. Here we've got, in this example, we've got multiple attributes associated with one subject. So our subject is this, www.example.org people-Fred. So Fred. So this is the thing that we're referring to, the subject we're referring to. And we've got three different attributes or three different predicates and objects associated with that. So his given name, the P colon given name, is Fred. His email, he has an email, which is this. And he's intending this meeting. Okay? And then here's an example of the meetings. In the meetings, m.homepage, here's the home page for the meeting that Fred is attending. Probably not the easiest way of seeing this, but this is basically how it writes out. Here's another example in RDF XML. So XML you're familiar with. This is just an XML file. And in this case, it contains RDF triples. So here's the various namespaces that are being referred to. RDF namespace, DC, Dublin core namespace, and a region namespace. Again, we've got a predicate, one predicate here, the example, which is the Wikipedia entry on Oxford, and we can see that it's got a title. Its title is Oxford, its coverage is Oxfordshire, its publisher is Wikipedia, its region of population has a population value. Okay. So these aren't meant to be read by humans. These are being read by computers, of course, which is either a bit not easy to. Okay. So the WC3 defines some standard namespaces to do with RDF and also the ontologies that go on top of them. There's one called RDF, one called RDFS, one called OWL, SXSD. We don't need to worry about the details of these. But these ones define some standard terminologies and relationships that are used by just about everybody. Okay, so it's sensible to have them standardized and set by the standards authority. So for example, the RDF namespace defines a predicate such as type, subclass of, class, inverse of, and property. So for example, this allows us to make statements such as the lit Shakespeare is a type of playwright. Yeah, Shakespeare is a type of play. Right? He's a playwright. Ibsen, the name Ibsen, is a type of playwright. He's a playwright. These are all playwrights. And because we can define, and these have standard meanings, you're familiar with classes and subclasses, it means we can start reasoning, use these to reason across the graph. So, and what they do is allow you to reason across the graph in sensible ways, but they also sort of put constrictions on the relationships that you can make between the objects in your graph. So for example, the RDF property object indicates that a resource should be used as a predicate and not a subject or object. Okay, so here, wrote is a type of RDF property. And that means that wrote can't be a subject, or shouldn't, in general, is not a subject. It's only a subject in this statement. But in the graphs, in your graphs, it can only act as a predicate. It can't act as an object or a subject, yep? Because it's effectively a verb. Same with part of. Part of is a property. You can only have that as a property. You can't use this as an object or a subject in a statement. There's many of these. Basically, they're kind of relationships. This is defining things as relationships. All right, we've done that. We've done that. So given that, that's the basic model. And I don't expect you, I mean, to be honest, I grip with my fingertips on this sometimes to understand it myself. But that's basically how the data is organized. But of course, to be useful, it has to be part of an architecture to deliver this. And very similar, and the architectures that you have are very similar to the web architectures that you're familiar with. So your triples, your RDF triples, all that, your information basically that makes up your graph, your logical graph, can either be stored in text files, just using one of those forms of serialization that I showed you. So they either just type directly in, or more often, or is that they're actually stored in a database, which may be called an RDF store, or it may be called a triple store. These are databases specifically designed to store this form of information and to distribute it. So they're a form of graph database. And the databases they store the triples, They'll import additional triples from text files or other places on the web. They're potentially involved in scraping and converting data from other locations. So if you've got a XML file being returned by a database, a standard database, you could write some code, or the RDF database may have code ready embedded for reading that tabular data, for example, returned by an API into triples. So it'll have an automatic conversion technique methods. So once you've got all your data into your database, you can do it does your graph merging. So it takes the triples that you've got and it'll merge them into a single graph. And then it will allow you to query across that graph using the Sparkle query language. And I can't remember, Sparkle stands for Sparkle Protocol and RDF Query Language. It's another one of these what are called recursive acronyms, where the acronym is actually embedded in the, so you expand Sparkle and you get Sparkle Protocol and RDF Query Language, and then you can expand Sparkle, and it's just a silly joke. And then you have applications which provide the interface onto your RDF store database, just like we have in. So it's, it's the same stuff, but you're just, instead of exchanging tabular data formatted in XML as you do most of the time, you're exchanging and dealing with triples. So Sparkle is your query language. So we've got a really simple graph here, James Dean and three films that James Dean starred in. And the Sparkle query language is just like SQL. It's similar to SQL, but you replace the part of the triples that you're querying with, that you're not stating as being fixed, with a question mark. So if we want to find out which films James Dean played in or was as an actor in, we want to undertake this kind of query, and we put it out like this. You write it like this: select question mark what, where, and then we've got this this query function where James Dean played in what. Okay, not going to go into any more detail on the syntax of that. So that's your equivalent of your SQL statement to return the three answers: Giant, East of Eden, and Rebel Without a Cause. Okay, so you've got a different syntax language where you replace the things that you're querying with what, question mark, and what. And these can get more and more complicated. Here's a slightly larger graph. We've now got the films that they've directed, who the directors were of the various films, and we want to know who directed the movies James Dean played in. We can do a query like this: select question mark who, where. The who is just and the what are just markers so that you understand that it's a who or a what, or a, to give some context to the query. It's the question marks that are really important. So who, where James Dean played in what, question mark what, directed by who. Okay, I mean, it's not easy to follow, I think. It's rather difficult. It's not as easy to read as SQL, but that's the query that you would write, and you would get these four answers. So that's the nut of the semantic web. That's the data side of it. But the semantic side of it is more complicated, or it sits on top of this. So this is the information. That's the information and how you combine the multiple graphs into a single information graph. But how do you give that meaning? Well, one of the ways that we've given meaning already is by the RDF statements like property of and subclass of and class of. They impose restrictions about how the relationships between various data items, whether you can generalize. If it's a class, a superclass, subclass, you can make generalizations on that basis. There are two things that add more and more semantic control over your data graphs. One of them is called RDF schema, RDFS, and the other one is called web ontology languages. And this basically layers more and more controls over your graphs, and the more controls you have on your graphs, the more highly structured your model is, which means that you can make different types of inferences. As your model becomes more complex, it controls what inferences you can make. So RDF schema is like RDF, and in fact, it's written in RDF, but it allows you to define a more complicated hierarchical class structure. So superclasses, subclasses, class and subclass of are two of the really important things that RDF gives you. And it also allows you to set restrictions on domains. So, domains on a relational database, your values can only be between 1 and 100, for example, or it can only have these sets of valid names in it. So RDFS adds that kind of thing. It adds domains and a more complicated class structures. Web ontology language, also known as OWL, adds even more semantic relationships. So things like inverse of, because remember these are directed graphs, so it allows you to define that the inverse is also acceptable. It does superclass, equivalent classes, same as. So it adds more and more semantics on top of your graph models. And this is a really simple example of the sorts of things that you can end up with when you've got both RDF and RDFS together. This doesn't include OWL as well. But we can see that, for example, this is for boats, various types of information about boats, so that we can see that an out-of-service vessel, one that's basically in the dock somewhere not being used, is either has a destruction date or a decommissioned data. So it has data on decommissioning or it has a destruction date. These are domains being imposed on the vessel. Okay, so here's the actual data on the individual vessels, and we can see these are mostly types. They're a type, they're a member of the class deployed vessel, or they're a member of the class out-of-service vessel. And as you can see, the Titanic is both a deployed vessel and an out-of-service vessel. It was never decommissioned. Obviously, it's at the bottom of the ocean. Okay, so once you've got these graphs, then you can make your inferences across them. Yeah. All right. Okay. So the geosemantic web. Geosemantic web is simply geographic data on the semantic web. And it started in 2003, so this is just over, 12 years ago. 12 years ago, roughly, a WC Semantic Web Interest Group created a basic geo vocabulary which provided a way to represent WGS84 points in RDF. Then 2003 to 2005, I suspect, they developed various what they called incubator groups to develop a geo-OWL representation for geospatial concepts and data structure. So they started developing a model for storing geographic data in RDF, RDFS, and OWL. Okay? But these have not developed into W3C standards, so it's still not a established standards. And the OGC working groups are still sort of working away, developing a standard RDF representation for geospatial data. But they have developed the GeoSparkle addition or add-on to Sparkle for querying geographic data, presumably the data structures that they developed in these incubator groups, but still haven't actually become standards. So they're working with sort of non-standardized, the things haven't become full standards yet. So Geosparkle. Oh, it's the Geosemantic Web is basically it shouldn't be Geosparkle, it should be a Geosemantic Web really. Is a vocabulary for representing geographical data in RDF, and it uses an OWL ontology for representing features and their geometry. So, for example, here's just a simple little diagram showing that the spatial object is made up of features and geometry, and the feature, a set of features, or a spatial object has both feature and geometry, and the feature has geometry. So with Geosparkle, you can undertake spatial queries, such as what are all the geometries within 10 kilometers of a particular feature, and in this case, it's the feature described by that URL. Okay, and you can write a query, something like this, or this is the query that will query the graph at swsgeonames.org. It will query this graph. So you set the web address of that graph. That's a RDF. That will be an RDF file on the end of that graph, or it'll at least return a set of RDF triples. And then we can do this, write this rather complicated query that actually returns us the other geometries in this graph that are within the 10 kilometers of the stated object. It's not friendly syntax. But then, you know, SQL isn't friendly when you start, but you soon pick it up. So where does this stuff, does it actually exist anywhere, or is this all just theoretical? Well, here's the Geosparkle engine. So this is well worth a visit, actually. So you can go here, and it's got various links to various RDF triple locations. I believe you can query roughly 3.6 million, or is it billion? I can't remember whether it's million or billion triples. There's quite a lot of them out there now. And you can go here and you can write queries, get the returns. They've got some, for example, some recent queries that people have written. So you can play about on here and see what you can do with Sparkle and how it works. So I'd recommend having a little look at that when you have a moment, Geosparkle. And this is what you get in return. So the query that we had up there, that's basically the default query. Run that. In fact, that is the query is that the query? No, that's a slightly different query. So in this case, we're returning link name, population, latitude and longitude, where it's within a certain distance of, presumably, within a certain distance of these coordinates, I think. And that's the sort of result that we get. And you could you can return it in XML, you can return it in KML, or you can return it in just a tabular format like this. OpenStreetMap has a Geosemantic Web interface, a basic one. So this is the same OpenStreetMap that you're familiar with, or reasonably familiar with, but the data is actually being stored and manipulated through RDF or Geosemantic versions of RDF rather than through XML. Okay, so little interface there onto the OpenStreetMap. This is rather out of date now, 2010, so that's September 2010. And this is a graph of the organizations that are presently serving what's called linked data. Now, linked data is a particular flavor of RDF in which every single item that you put into the graph must be a URL. Okay, so everything is defined by URLs. And you can see that there's quite a lot of organizations provide information in this format. The BBC do quite a lot, Last.fm, government sites. There's not a huge amount of what you could call true geography, but GeoNames is one of a very collected central one. DBpedia, which is a sort of database version of Wikipedia. I'm not really that familiar with it. Is another, is pretty central to this graph. But you can see the various, there's quite a lot of organizations that link into this. And I must say it's the kind of data, once your data gets into millions and billions of items of data, then linked data and the semantic web starts to become a really, potentially really useful set of technologies to help manage and these data and combine data from these different data sets. Is that the OS? Yeah, looks like the OS are producing some as well. Okay, so there's a lot of data out there increasingly. Look at it, the life sciences have particularly taken up this, the use of linked data, but also publications, the publishers have also are big uptakers of linked data. So we're just kind of, so that is one, I think this is one small section of the whole internet which we kind of started with. So this is, despite this linked data exists within the internet just like the web pages exist with the internet, just like the APIs exist with the internet. They are part of the internet. I just want to finish off the web part of this course with, I don't know whether any of you, have you seen this before? This is called the Internet Mapping Project. And it's quite, from a user perspective, it's quite interesting. So people, basically, they went out and said to people, I think you can do this on the internet, draw a map of the internet as you see it yourself as an individual and put your home on it. And if you think from user perspectives of the world, this is I think this is quite an interesting way in which people, to explore how people see the internet, different people see the internet. And this is your classic map view of the internet, college test proctor, whatever that is, but age 39, we've got, oh dear, we've got a sort of map with a, map is taken a map metaphor. We've got Amazon, we've got Netflix over here, we've got the various places that the person uses on the internet, and we've got it depicted by, basically with a map metaphor. YouTube down here, etc., etc. But other people look at the internet in a very different way. And these are just 4 that I picked up off the other day. So this is again a sort of map metaphor, but it's more like some kind of shopping precinct than it is a landscape that the person goes across. It's more like on a high street view or something like that with various signs. It's not all connected, but there's signs to where you can only see a certain what's immediately around you. You can't, the other person had an overview. They had an overview of what the internet was and how things connect. So in another, this person is very much about, I'm here, which direction do I go from here? So that was somebody who was 20. This is a 12-year-old. Obviously spends rather too much time, I suspect, on the computer. The eyes are going. They've got sort of, the brain is being fried. There's these strange .edus, .orgs spread about, and then there's all these various pages, but there's not much connection between them. I really like this one, 40. I imagine this is sort of depicting how their journeys are. They start and then they go out and then they stop or something like that and they go back. I don't know, but it's quite an interesting view. It shows that it's not one thing. People don't see it as one thing necessarily. They go in, they do something, they come back. They maybe slide off in a different direction for a while, but there's isolated usages. And then this was a writer, 46. That's his home, in his head. And the internet is an extension of his own brain, I guess. That is the sort of the idea there. But I just like those. They sort of show how, when you understand the technologies, you can make so many assumptions and you forget how other people see the world quite often, because and this is the same no matter what we do. If you're embedded in something, you're an expert in something, you forget what it is not to be. And you forget that people with different life experiences just deal with the world and live.